Hello class. So today we're going to investigate some level 1 material. I've kind of been hinting at it over the past week, but we're going to dive into it now. So regardless of whether you're level 1 or level 2, we're going to watch this full video in order to get an understanding of two different concepts. One of which is going to be how to find the average mass that we find on the periodic table. I've kind of talked about it a little bit before, that there are different isotopes of different atoms, such as with carbon, there's carbon 12, 13, and 14. So we're going to find out how those numbers on the periodic table for the atomic mass got there. And then second of all, we're going to learn how to use the electron orbitals, those numbers that we haven't really known what they were on the periodic table. We're going to figure out what they mean and how to use them to determine Bohr diagrams of any element. So, we have two different isotopes here. We have 35 chlorine and 37 chlorine. We're going to figure out how we got the average chlorine on the periodic table. So what we need to do first is identify the atomic masses, 35 and 37. It turns out that there are 75.5% of chlorine 35 in the world, while there's about 24.5% of chlorine 37 in the world. So we're going to use these averages to figure out the parts of each of these chlorines that contribute to the average. So if we take the atomic mass of the chlorine 35 and then multiply it by the percent of which it exists in the world divided by 100, so essentially it's decimal equivalent, so here 0.755. We multiply these two values together and then add the 37 multiplied by its percent proportion here. So by 0.245, we add these two values together and we get 35.5. If we look on the periodic table, that's the atomic mass of chlorine. And that's how people found it and eventually put it on the periodic table. Let's now look at this example with 238 uranium and 235 uranium. You've probably heard of this element uranium. It's used typically in nuclear power plants. And the 238 uranium is a lot more abundant. There's 99.3% of this 238 uranium, and there are about 235. Of the 235, there's about 0.7%. So let's pause the video at this point and try and do this problem. Okay, let's look at the answer. If we take the 238 and multiply it by the 99.3 divided by 100, so essentially it's decimal equivalent, we get this quantity here. We then need to add to it the same thing but using the 235. So taking the 235 and multiplying it by the 0.7 divided by 100, we get this quantity here. Adding them together, we get a final value of 238. And if we look on the periodic table, that's the value that it is, so we know we did it correctly. Let's look now at orbitals and energy levels. So this is a hydrogen atom, and we should be pretty used to these types of diagrams. This is just a typical Bohr diagram. The problem with a Bohr diagram, though, is that it simplifies where the electron is. Here, it's just saying that the electron falls in this perfect circle around the nucleus. But as we talked about a little bit in the beginning with the history, electrons just don't go in those perfect circles. Instead, they tend to go in these electron clouds, and they can be anywhere inside of that cloud based off a probability distribution. So, we've designed these things to help try and understand these complex probability densities, and they're called orbitals. There are 4 different orbitals that we use to help model this complex cloud phenomena. We have s orbitals, p orbitals, d orbitals, and f orbitals. The way I have it marked here on the periodic table shows the sections of the periodic table that first occupy that orbital. These orbitals have subsections as well. So there's a 1s orbital, a 2s, 3s, all the way down to 7, 2p, 3p, all the way down to 6, and likewise for the d and f orbitals. So what do these orbitals really mean? So let's look at them. Let's first look at the 1s and the 2s orbital. The 1s orbital is the first orbital, and it holds 2 electrons inside of it. The electron can be anywhere inside of that cloud, but it's bound to it. Looking then at the 2s orbital, as you can see, it circles around the 1s orbital. It shows where the electrons would be. Kind of like the Bohr diagrams, how the second ring goes around the first ring. We can think of the second steps of the orbitals as a little bit farther out, but forming a shape around the first one. They're not all perfect circles though. The 1s orbital and all s orbitals are spheroid orbitals. The p's form these kind of disc-like structures, and the d's even get more complicated, especially with this guy. We don't have to worry too much about their shapes, but we do have to understand that these orbitals aren't perfect circles around the nucleus. Instead, they're zones in which the orbitals can occupy instead. The s orbital can hold 2 electrons. And this is every s orbital, the 1s, the 2s, the 3s, all the way down. All the p orbitals can hold 6 electrons, d orbitals can hold 10 electrons, and f orbitals can hold up to 14 electrons. So let's figure out how we know which orbitals an element has and how this information is useful. Let's look at neon. We know that neon has 10 electrons when it's at an uncharged state. Let's now see which orbitals it ends up taking up. We can use this diagram here to see the orders in which we fill in the orbitals. It's pretty intuitive. In this first column, we write 1s2 all the way down to 7s2. Here, just one step below, we have 2p, 6, and we write it all the way down to 7. One step down again, we draw 3d10, and all the way down to 6d. Again, one step down, now in the fourth period, 4f14, and down here to 5. Following the arrows, we see the order in which we fill them up. So we start out in 1s2, then we go to 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and we can follow the rest of the arrows. We can use this as our guide to see in the order in which orbitals we're using to fill up an electron shells. If we look at specifically neon, we first get our first 2 electrons from the 1s orbital. So right here. We've only gotten now 2 of our 10 electrons. So now we follow the arrows and go to the next one. 2s2 gives us another 2 electrons. So now we've hit 4 out of our 10 electrons. We then need to go to the next step to 2p6. With that 6, we've now reached our 10. We now have all the electrons. We've used the 1s orbital, the 2s orbital, and the 2p orbital. We can use this information to then do other elements such as phosphorus. Now we're going to be looking at this electron configuration on the bottom. As you can see here, it says neon, and then it has 3s2 and 3p3. We just figured out the electron configuration for neon. We said it had a 1s orbital, the 2s, and the 2p filled. Phosphorus has those filled as well as 3s2, 3p3. Since both the 3s2 and the 3p3 have the 3 in front of them, they both are a part of period 3. That means in period 3, we have 5 electrons. The 2 here and the 3 here. So we filled up everything in the first electron energy level with the 2 electrons from the 1 sp2. We filled up the entire second ring of the electron, the 8, using the 2 from the 2s2 orbital and the 6 from the 2p6 orbital. And then now we've added an extra 5 electrons to the third electron energy level, having these 2 electrons from 3s2 and these 3 electrons from the 3p3. And this makes sense from all the other times that we've drawn Bohr diagrams for phosphorus. We have 15 electrons, so that's 2 in the first shell, 8 in the second, we fill those up, and we have the 5 left over. All these orbitals are telling us are the specific locations of the electrons, but it relates back to our previous knowledge. Let's now look at a much more complicated example and see if we can use these skills to work with that too. Looking at iron, this is something that falls within those transition metals, something that we haven't worked with before. But we can use the electron configuration here to help us. Here we have the argon, and we know, past argon, what electrons go in the different shells. We know that it's occupying the 4s2 and the 3d6. Note though, as a transition metal, it's occupying both a shell that falls in the 4 period and period 3. So, let's pause the video now and try and do this problem. It's gonna be pretty hard, but we can do it. So pause the video now, and I'll show the answer after you unpause. Okay, let's look at the answer. The protons and the neutrons should be nothing that's too complicated. That's the same as before. The only weird part now are where the electrons go. If we followed along, we should have electrons in the 1s2 orbital. And that's why we have electrons here. We also have the 2s2 and the 2p6, thus occupying here. We had occupied also the 3s2, the 3p6. We went on to the 4s2, but then we came back to the 3d10, but we only added in 6 electrons. So we came back to an orbital because the electron configurations were telling us to do so, because of that 3d6. So we've now drawn this diagram for iron, and we have a lot more examples in the worksheets that should have been handed out to you guys. So good luck, guys. If you have any questions, I'll be back on class on Monday.